In this video, we will work through problems related to volume and surface area. Consider a box that has length L, width W, and height H. Then the volume of the box is given by the formula length times width times height, and that's how much material can be contained inside the box. Now the next concept, surface area, is the amount of material that it would take to construct the box. And the surface area for this formula comes from the amount of area in the face of the box that's facing the screen, plus the amount of area from this portion of the box, plus the amount of area from the very back portion, plus the side portion, and then finally plus the top and the bottom area. Now each of these areas were areas of rectangles, and we know area of rectangle is the length times the width. So for instance, for the length here, we've got it's made up of width W and height L. So that'll be W times H will give you that area. Symmetrically, that's the same for here. So we have the first portion of our surface area, and that takes care of these two boxes, or these two sides of the box. Now let's do the front of the box and the back of the box. Both of them symmetrically are rectangles where we've got length and height. We know area of a rectangle is side length times side length, so length times height, and you've got two of them, one here, and then symmetrically one of the exact same type behind it. So that will add a 2 length times height. And with this, we can find the formula for the surface area of any kind of rectangular box or prism. So the volume is just length times width times height, and then surface area is the area of all the faces of the box added together. Next, let's consider a cylinder. Probably our most common cylinders that we've seen in our everyday lives would be cans of soups, cans of sodas, that kind of thing. And in a cylinder, there's two aspects that make up its shape. That is the radius of the circular base and the height of the cylinder. Let's mark that on our figure. So the radius is the distance from the center of the circular base out to the edge of the circle. And then the height is the vertical height of the cylinder. Once we know these, we can find the volume of the cylinder. The volume of the cylinder will be pi r squared times h. Now, if we recognize this first portion, pi r squared, from our previous lessons, pi r squared is the area of a circle of radius r. So what that's doing is it's getting the area of this circle, and then by multiplying it by h, imagine we're taking this area and lifting it up through the entire figure up to height h. That's what gives us the overall volume, or the overall amount of material that we can enclose in the can. So we know volume is the amount of material that the space encloses, and then surface area is the amount of material it would take to go along the outside of the shape. So for us, if we were to find the surface area of this cylinder, if you can't envision with me, there's kind of two aspects to the material that creates the cylinder. We've got the material that creates the circular top and the material that creates the circular bottom. And you know the area of a circle is pi r squared. So the fact that there's a circular top and bottom means we would need 2 pi r squared worth of material to create the top and the bottom. And then to create the material that goes on the outside portion of the cylinder, in order to envision that, we need to remember the idea of circumference. Now we learned in a previous lesson that the circumference, the distance around the outside of a circle, is 2 pi r. And if you can imagine, take this distance around the outside of the circle and then lift it up height h, because it's that same distance all the way up to the top of the can. So if we continue to have that same distance lifted up by height h, then we find the material that takes up the outside of the can is 2 pi r for the circumference times h across that height. So we've got a formula for the volume of a cylinder and the circumference, or excuse me, the surface area. So in our next example, we're asked to find the volume to the nearest cubic inch. of a cylinder with a diameter of 8 inches and a height of 6. Let's draw this cylinder first. I encourage you to pause the video right now and draw a sketch of the cylinder based on the description. Unpause to check your work. So we know the diameter is 8 inches, so this entire distance all the way across the circle is 8 inches. And the height is 6 inches. So we know the vertical height is 6 inches. Now if I want to find the volume or the surface area, in this case I was just asked for volume, but looking back at these formulas, they both require us to know about the radius. Now I was given the diameter, so the first thing I'm going to do is convert the diameter, being 8 inches, means the radius is half the diameter, so that's 8 divided by 2. We've got a radius of 4 inches. Now we can use our volume formula. The volume is pi times the radius squared times h. Now keep in mind in our class that whenever we use pi, we use the rounded version of 3.14, so everybody has the same answers. So 4 squared is 16 times 6 for the height times 3.14. Let's type this into our calculator. And we get 301.44. Now we know the units of area are squared units, but the units of volume are cubic units because you've got a unit squared times the other unit, so that's inches squared times inches would give us inches cubed. So next will be the volume and surface area of a sphere. Whenever we think of a sphere, think of like a globe or a ball, and what it is it's got a center point, and then the way we define a sphere is any point from the center point out to a surface of the sphere is exactly a fixed radius r, and that will work in any direction. So from here to the outside of this circle, or sphere, is also r. From the center point to any distance on the edge of the sphere is always distance r. Now we've got two formulas, one for volume, one for surface area. The volume formula is 4/3 pi r cubed, where r, the radius, is the distance from the center out to the edge of the sphere. And then the surface area formula is 4 pi r squared, where again r is the distance from the center out to the edge of the sphere. So here we're told a basketball, which when we think of basketball we should think of sphere, has a radius of 4.5 inches. If the ball is filled with 350 cubic inches of air, is this enough to fill it completely? Now let's think about what we've been given here. 350 cubic inches of air, and they filled it. This is the idea of filling the inside, which if we think about our phrasing earlier is a volume characteristic. Additionally, I could know it was a volume measurement because we're dealing with cubic inches, and we know volume has to deal with units cubed. So they've said they've used 350 inches of air. Is that enough to fill it completely? Does that max out its volume? Well, we could find the volume of this basketball by taking our radius and saying the volume of the basketball should be 4/3 pi times the radius of 4.5 cubed. We know when we type this into our calculator, it'll be 4/3 times our rounded version of pi, 3.14, times 4.5 cubed. Okay, let's calculate this together. So I found 4.5 cubed is 91.125. Multiply that by 3.14, then multiply that by 4, and divide it by 3 to get 4/3 times that. And we get the volume is 381.51 inches cubed. So the amount of material that can fill up this basketball is 381.51 inches cubed. Now we've used 350 cubic inches, so we see there's still room to spare. There's about 30 or so cubic inches left of space. So let's just write this out. This is not enough to air up the basketball completely. Okay. So we just write our conclusion that since the volume of the basketball is 381.51 cubic inches, the 350 cubic inches of air is not enough to fill the basketball completely. Next, let's look at volume and surface area of a cone. So in this circular cone, it's a cone with a base that's a circle. We have that the volume formula is equal to pi r squared times h over 3, where r is from the center of the circular base out to the outside of the circle. That's our radius as before. The height is from the top of the cone down to the center of the cone, down to the center of the circle. So that's the volume. And then the area, the material that makes out the outside of the cone, that can be found from this formula. Pi r squared, we know that pi r squared, that's the area of the circle. And then to figure out the area of this outside portion of the cone, that comes from the pi r times L. Now what is L? This L is this distance here, which if we visualize carefully, we can see that happens to be the hypotenuse of this right triangle. Now we know the hypotenuse, the distance here from the center out to the edge of the circle is radius r. So L is, by solving the Pythagorean theorem, equal to the radius squared plus the height squared. And that's how we'd find the formula for the surface area of a cone. Next, we're asked to find the volume to the nearest cubic inch of a cone with radius 4 inches and a height of 6 inches. I'd encourage you to pause the video right now and sketch out this cone on your own, based on the fact that the radius is 4 inches, the height is 6 inches. So we have our cone here. We know the radius is the distance from the center of the circular base out to the boundary of the circle, so that's our radius r. The height is from the point of the cone down to the center of the circular base, that's 6. And if we're asked to find the volume, we know the volume formula from above is the volume of the cone is pi times the radius squared times height divided by 3. Now for us, we know we use pi as our rounded 3.14. The radius, I should have labeled this in the diagram, the radius is 4 inches. So that's 4 squared times a height of 6 over, the formula says divide by 3. Let's calculate this. And when I type this into the calculator, I get exactly 100.48 inches cubed as the volume of this cone. Let's continue with the volume of a pyramid. Now consider a pyramid with a rectangular base. So here's the base of our pyramid, and then we have, going up to some height, the highest point of the pyramid. And then from that high point, we go down to the edges of the pyramid. And we see each of the sides of the pyramid. We've got the rectangular base, but the sides are all triangles. Now, in finding the volume of the pyramid, the formula says that it is 1/3 times capital B times the height. Now, the height of the pyramid is the height from the peak down to the flat surface. That's our height. The capital B comes from the area that is the base of the pyramid. So for the one that I've drawn here, if it's a rectangle with length and width, our base would be length times width, because that's what makes up the area of this base. So for a pyramid, we can find the height from the peak down to the flat base of the pyramid. And then based on the shape that the base makes up, you find the area of that base, multiply that by the height, and times 1/3, and that will be the volume. So in our next example, we're asked to find the volume of a pyramid that is 4 feet tall, and we're told that each side of the square base has length 6 feet. So in this particular pyramid, the base is a square. Let's first draw a sketch of this pyramid. I'm going to start with a square, and we were said each side of the square was 6 feet, so this is 6 feet by 6 feet. And then the pyramid continues to a height. And in particular, whenever they tell us the pyramid is 4 feet tall. That means at its highest point, so from here down to its base, is 4 feet tall. So if we were to find its volume, we know the volume is 1/3 times b, which is the area of the base, times the height. And for our particular example, that will be, our base is the area of a square, which is side length times side length, 6 times 6. The height is 4. Typing this into our calculator, and we will get exactly 48 as the volume. We know volume is in cubic units. We measure length in this problem by feet, so our units are feet cubed. Now let's consider our next two examples together. I'm going to read the first one and then the second one. In order to determine the amount of liquid a spherical tank would hold, would you use volume or surface area? Okay, before we answer that, let's look at our next question. In order to determine the amount of material needed to manufacture a ball, would you need to use volume or surface area? Now think about these two questions. I'd encourage you to pause the video now and make a guess for each of these two questions, and then unpause to check your work. Now keep in mind, volume is the amount that the shape can contain within itself, and surface area, a way we could think about that, is the amount of material we would need to construct the shape. So if we're figuring out how much liquid a spherical tank would hold, that's how much can it keep inside of it. That's the idea of volume. If instead we're trying to figure out how much material would cover the outside of something to manufacture it, how much material would you actually need to make a ball, that's the idea of surface area. So we just want to keep these two concepts distinct. Again, volume is the amount that the shape can contain on the inside. Surface area is the amount of material it would take to construct the shape from the outside surfaces. So in this next example, we have a spherical tank, which is 2 meters in diameter, can be filled with the liquid for $300 in total. Find the cost to fill tanks with diameter equal to 6 meters. In order to do this type of problem, it tells us information about a smaller tank, and then it asks us to extrapolate that out to a larger tank. We need to understand the idea of unit cost. So we're going to use the information given for the smaller tank, and once we get the unit cost from that, we can extrapolate out to the bigger tank. So let's first focus on the unit cost and how much volume is in the smaller tank. So it was said that it's a spherical tank, so I know I have a sphere. So I draw a quick sketch of a sphere. I know the diameter is 2 meters, but if you look back at the formulas related to sphere, they're all about radius. So immediately I want to change this diameter measurement into a radius. We know radius is always half of the diameter, so the radius is 1. So my radius here is 1. Looking back, we see the formula for volume of a sphere is 4/3 pi times r cubed. So for our particular sphere, we're looking at 4/3. We know we use pi as our rounded 3.14, and our radius is exactly 1, and we cube that. Now let's type this into the calculator to get the volume of this smaller sphere. And we get this answer as our volume. So that it's easier to work with, let's round to 3 decimal places for our later calculations. The volume is 4.187 cubic meters. And we know for this amount of material, it cost exactly $300 to fill it. Now we can always find the unit price by taking the cost divided by how we're measuring the units. And in here we're measuring the units of volume because it's how much it takes to fill. So our unit price will be 300 divided by the volume, which is 4.187. Let's type that into our calculator. 300 divided by 4.187. and that gets us exactly 71.65, and our units are the units at the top, which is dollars, per units of volume in the bottom, so that will be $71.65 per cubic meter. So for every cubic meter that we fill up of this material, it cost us $71.65. So all we need to do to complete the problem is to figure out what's the volume of the larger sphere and then multiply that by the unit cost. So let's find the volume of the 6 diameter spherical tank. We know for the larger tank it has a diameter of 6 meters, which means it has a radius of half of that, which is 3 meters. We have the same volume formula from before. It is also a sphere. Our volume is 4/3 times pi times the radius cubed, and for our particular problem this will be 4/3 times our rounded version of pi, 3.14, times 3 cubed. Let's type this into the calculator, and we'll find the volume of the larger tank is exactly 113.04 meters cubed. So that's the amount of material it would take to fill up the larger tank, but we know each meter cubed of material costs $71.65. So to find the total cost of the larger tank, we take the amount of material it would take times the unit cost of the material. So our final answer can be found to be the amount of material times the cost per meter cube of material, and we get an overall cost of $8,099.03.16. So let's round that to 2 decimal places. And we get a total cost of $8,099.32. So the key aspects to this problem is we are given information about the cost to fill up a smaller sphere. From that, we were able to fill up the unit cost. How much does this particular material cost per cubic meter? Once we found the unit price for this material, we could then, if we knew the volume of the larger tank, take that volume times the unit cost and get the cost of filling up the larger tank's material. So always remember the idea of unit cost. That is cost divided by however you're measuring it. And in this case, we are measuring the difference between the two tanks in their volume. So in this next example, we're asked to find the volume and surface area. The first step to that is just to identify what type of shape are we looking at so that we can go back in our notes and find the correct formula. Looking at this shape, we see it's a very squished can, or a circular cylinder. So if you look back in your notes a few pages before this, we can find the formulas we just wrote down. The formula for volume is pi r squared times h, and for a cylinder, the surface area is 2 pi r squared plus 2 pi rh. Now in this figure we see clearly that the radius is 12 meters and the height is 4 meters. That's labeled in the figure. So all we have to do is correctly calculate each of these. We know we're going to use our rounded version of pi, 3.14, times our radius of 12 squared times our height of 4. Type that into the calculator. And we get 1808.64. Let's look at our units. Our length is measured in meters. Volume is cubic units, so this is meters cubed. And I would encourage you to take a moment and pause and attempt to find the surface area on your own, and then unpause to check your work. So pause the video now, figure out the surface area, unpause to check your work. We know for surface area it's 2 times our rounded version of pi times our radius of 12 squared plus 2 times our rounded version of pi times my radius of 12 times 4. And as these are two different things, particularly my on-screen calculator doesn't have parentheses, so I'm going to calculate these two separately and then add the two pieces together. So as I do this, the first calculation gives me 904.32, and then the second part of the calculation would be 301.44. Adding these two together, and we get exactly 1205.76. Now for area, surface area is the material it would take, so that's going to be a squared unit. Area is units squared. Now just for practice, if we were figuring out how much material this can could hold, would that be a volume or a surface area? So how much material can the can hold? That would be a volume. This material can hold exactly 1808.64 meters cubed of material. If instead I ask the question, how much material would it take to construct the can? So how much tin would we need? That would be exactly the surface area, 1205.76 meters squared of material. Now this last example takes the material one step farther. It has the idea of volume, but if you notice as you look at what's drawn in the figure, some of the side links are labeled, but we don't know what they are. Instead of labeling this side length as a value, instead it's just labeled as x. And instead of labeling this side length as a value, it's listed as x minus 1. Now we do know the height of this pyramid. We were told that's 15. So we have a little bit of information. So after we've familiarized ourselves with the picture, let's read the example. It says the figure below has a volume of 450 meters cubed. Find the value of x. So our goal in this example is to just find the value of x. Let's list out what we know. We know the volume is 450 meters cubed, but we also know this is a pyramid. And if you look back in your notes, you have a formula for the volume of a pyramid. Looking back in our notes, we see the volume formula is 1/3 the area of the base times the height is the volume. Now we can fill this in for what we know. We know the volume is 450. We know the height is 15. And although we don't know a number for the area of the base, I think we could at least express it abstractly. The base of this pyramid is a rectangle. And you know the length of the rectangle is x. You know the width is x minus 1. So that gives us the area of the base is x times x minus 1 times the height of 15 times 1/3 in the formula. All of this together is said to be 450. So because we were told the volume is 450, we were able to write down the volume formula, and then based on the figure, plug in a lot of the known pieces of information. Now let's simplify this. Right off the bat, 1/3 times 15, if you type that into your calculator, that is 5. So this becomes 5 times x minus 1 equals 450. And if we're trying to get x by itself, my goal would be to first get the side with x's just with x's. So let's get rid of this multiplication by 5. We will divide both sides by 5. Whenever you divide 450 by 5, you get exactly 90 is equal to x times x minus 1. Now, I think the setup of this problem is very reasonable. It comes down to it that solving this is a little more difficult than what you would be expected to do in our class, because our class doesn't focus on factoring, which you would need to solve this problem. So I hope that the setup makes sense, but in terms of actually solving it, we're just seeing this as an interesting problem. Don't feel like you're expected to be able to solve at this level. However, let's still continue the problem so we can think through it, because I found another way that we could introduce it without factoring. If I distribute my multiplication on the left side, the right side, I would get x times x is x squared minus 1 times x is x. Now, if we're just thinking about integer answers, we have to ask ourselves, what when squared minus itself gives me 90? Well, let's think. If x was 2 squared minus itself, that's 4 minus 2 is 2. Nowhere close to 90. Okay, let's go up one more. Let's now think, what if x was 3? 3 squared minus itself, that's 9, minus itself is 6. Nowhere close to 90. We need a number that when we square it gets us pretty close to 90. Can you think of an integer when squared that gets you very close to 90? Maybe you thought of 9, because 9 squared is 81 minus 9. Well, 81 minus a number, that's not going to get you to 90. You're already lower than 90. Let's think of the next integer up, 10. If x was 10, 10 squared minus itself, that's 100 minus 10, that is 90. So we've been able to figure out through a little bit of trial and error that the distance x is 10. So this other side length, 10 minus 1, is 9. So we figured out x should be 10. Now that's one method. Let's also go over a method in terms of factoring. If you've seen factoring before, this might be a nice review. If you haven't seen factoring, again, remember, this portion of solving for x is just an extra problem. It's not going to be something you're tested over because our class does not focus on factoring in terms of solving algebraic equations. So we've already found the answer is 10 through trial and error. But if I was to try to solve this mathematically using factoring, I know factoring only works whenever one side is equal to 0. So I would first subtract 90 from both sides. That gives me a 0 on the left side equals x squared minus x minus 90. And if we've done some factoring, we know we start with x, don't know what comes next, times x, don't know what comes next. But we can look particularly at the sign here. Since this is negative, the only way you get a negative sign on the constant is if you had one positive and one negative, because positive times negative is negative. And then we think, okay, what numbers could multiply to give me 90, but somehow add in a way to give me negative 1? Okay, so negative 90 multiply, but the terms add to give you negative 1. I think maybe negative 10 and positive 9. So negative 10 times positive 9, that gives you negative 90. But then 9x plus a negative 10x would give us a negative 1x. So we factored this equation, and you know the only way something times something equals 0 is if the terms separately equal 0. So we think about, when is x plus 9 equal to 0? Well, that would happen when x is negative 9, but that doesn't make sense in context because we're talking about lengths which need to be positive. So when could the other term be equal to 0? X minus 10 equals 0 only occurs when x equals 10, which was the answer that we found previously through kind of our guess and check method. So that's it for this example. Again, remember, solving something like this is not something you're tested on. This was just kind of an extension problem. So as always, if you have any questions about these topics or volume and surface area, please reach out to me through our Canvas or our campus email, and I'll be very happy to answer your questions.